Good morning, fancy meat computers. How is everybody today? Doing okay for a Thursday, I hope? Hopefully. Good morning. Yeah, we finished that. All right. Good. Long day ahead, but I'm all right. Yeah. Tell me about it, eh? Hmm. Just give it a minute for the rest of the class to show up. I don't know. How many people are there? Is there anybody in Hamilton Hall listening in today? Hmm. All right. Well, I guess we might as well get started then. So, last time we were talking about file input output. Today we will be talking about data structures. This is kind of our last big C programming topic. So I hope that everybody's paying attention because this will be on the test. So, data structures. We're going to learn about structures in general, the struct construct, as it were. We're going to do we're going to have a little bit on bitwise as well, and 2's complement, just because that stuff is very useful. Then we're going to talk about some data structures like data structures proper type stuff that sort of very similar to the stuff that I'm talking about in the other class I'm teaching, the data structures class. Just a little bit. Just a taster. You guys do have a whole course on that kind of stuff coming up next semester, which apparently I've been in contact with the professor who's teaching it. He's going to be doing C++ in that course, so he has kindly requested that I pivot the course material away from this stuff, which is kind of generally useful C programming stuff, and towards a couple of things that I used to cover on C++ programming. So yeah, I think that's fair. So when we get through this material and the assembly programming material, we will cover some C++ material to the extent we have time for it. So I'm going to have to motor, though, to be able to get to it. So, structs. So let's talk about structuring our lives. So, up to this point, we have had no abstraction mechanisms besides functions in C. Consider the following scenario. Let's imagine we have a database that contains the names, email addresses, and pinball high scores of customers stored as a CSV file. So, perhaps we have John Boring, Sally Plain, Nancy Snore, and Peter Bland, and, of course, Themarius the High Elf. We could group this data by field into arrays. So have one array for names, have an array for email, have an array for pinball high score, and then, assume that the indexes, like index 3, will be one consistent entry. Or we could use a better method, which is to create a structure data type, to create a record for this data. A structure groups several variables together into a single data type. Structures are roughly analogous to classes in Python if you remove the methods, which of course means that it's not like classes at all. So yeah, basically this thing that classes do where you are allowed to store several different fields inside of one programming construct and then instantiate as many of those as you want, or even create arrays of them if you really want to. This is what we're talking about with structures. So consider the following structure. Struct customer has a char star name, char star email, and int pinball. This creates a new data type customer with fields name, email, and pinball. So the correct way to think about this is that you are constructing a new compound data type. This means that the term customer may be used anywhere you use any other data type in your program. Arguments to functions can be of type struct. Variables can be declared of type struct, right? Or of type customer in this case. When you're trying to decide how big things are, you can use size of customer, and that will return basically the size of this plus the size of that plus the size of that, plus any gaps that might be in between in the binary representation. So, the fields of the structure are accessed through dot syntax. So, now that we have our structure declared, we can say struct customer maboys of size 5. So we are declaring an array of size 5 where each element is a customer structure. We then may say maboys at 0 dot name is John Boring. Maboys 0 dot email is equal to johnboring at whatever.com. And you can do similarly with integers. So you can do assignment through dot syntax. If you did any degree of object-oriented programming in Python, this should be a fairly familiar construction for you. So in addition to being able to directly assign to and from, read and write to, shall I say, these structures which are contained in the array, we may also initialize them in the same way that we would an array, except now the various elements are allowed to be different data types, but they have to line up with the data types as declared in the structure and may not exceed the number declared in the structure. Any questions so far? Give me a thumbs up if you're following. So, one thing that's a little bit awkward about using structures, if you don't do anything else, What's the @0 for? Oh, thank you. So this @0 is because MyBoys has been declared as an array of customers. So this is just the first element of the array of customers, right? If this were not declared as an array, you could just say, you know, myboy.name, myboy.email, myboy.pinball. Yeah, you could just use that bit. Does that make sense? Hopefully. So, when we use a data type declared with a structure, if we don't do anything else, we have to use the struct keyword every time to preface the data type. Tell C that we're talking about a struct. However, awesome, we can get around this by including a type def, which renames struct customer as customer with a capital C. This is like the normal convention. So if customer has a capital C, right? Like generally data types are custom data types are capitalized. That's convention, although it's not required. Remember what type defs do. They take everything up to and everything up to, but not including the last identifier, and collect those all up as one thing and give it the name of the last identifier. So, if you would combine this type def with the structure declaration, that means you can just say customer myboys instead of having to say struct customer, which saves some time and is a little less painful. You can also define a default structure variable as follows. You can say custdef, that is to say customer definition is something like none, none, 0, right? So then, this defines a predefined structure with values, which you can pop in anywhere you want. So, for example, customer myboys is an array of 5 customers. We can initialize that as the initialized definition of customer 5 times, and boom, that blows out all the garbage data. Question: out of curiosity, would you ever be given a pointer within a structure, like star myboys +1 dot name John Boring? The reference myboys +1. Yeah, you could. So you're kind of jumping ahead a little bit in terms of the content, but you know, since the question was asked, so the question is, like, in general, what's the interaction between structures and pointers, right? So let me just grab a notepad and let me just hammer this out. So let's imagine that this notepad is like something like my computer's memory system, right? So inside here, this is my computer's memory system. So the way that a structure gets declared, right? Some point in your memory system is selected, and you have contiguous fields included for all of the fields of the struct. Right? So that's just if you declare a single customer structure, that's what you have just hanging out in your memory, right? If you declare an array of these things, right, it just puts a bunch of them adjacent to each other, right? So, let me just linearize this somewhat so that it's a little less horrible. Let's just imagine we have 3, right? So, if you have something like my boy right here, which is, or, you know, just a struct that's hanging out in the middle of nowhere, right? You can have a customer pointer, you know, C pointer is equal to address of my boy, right? What that does is it takes this, right, in the same way that a pointer to an array is a pointer to the starting address of that array. A pointer to a structure is a pointer to the starting address of that structure. So basically, it finds the beginning of the structure, right? It says, okay, this is the address that's beginning, that it begins on. It oh, I forgot the ampersand. There, ampersand. It substitutes my boy for this memory address, right? And that becomes the value of C pointer. So, if, on the other hand, this thing is an array of structures, right? The same basic rules apply. However, if you want to jump, like if you add 1 to this pointer, remember that it's jumping by the size of the elements of the array in terms of memory addresses. So the size of this guy right here, that's not only is that what like size of returns is the size of this segment in memory, right? When you add 1 to this pointer, it scoots it over that far to the next element in the array of structures, right? So it's completely and totally possible to traverse an array of structures in the exact same manner that you traverse an array of anything else. The sort of operational semantics don't change, right? And, you know, the question, of course, is once you have access to one of these structures in the middle, how do you get information out of it? And the answer is through dot syntax, of course. But the idea of using pointers to traverse the individual elements within the structure, that's not something I would expect you to want to ever have to do. It's highly, highly dependent on the structure of the structure, if you forgive the pun, or forgive the choice of words there. Like, name, email, and pinball are all going to be fields of different data types, right? At the moment, you know, this one's a pointer, this one's a pointer, and this one's an integer, right? So it's totally and 100% possible that the user may choose to insert additional fields, right? Like maybe Donkey Kong high score, which is also an integer, and just insert that into the middle. If you have written your program such that it's accessing the fields of a structure through pointer offset, which incidentally is possible, it is a thing you can do, but if you do that, it means that your structure, if your structure changes in any way, shape, or form, your program instantly is destroyed. And this sort of cuts against the idea of modularity and code reuse, which is, of course, the cornerstone of good software design. So, when you want to access the individual elements of a structure, use dot syntax. Okay? Good? Hopefully? So yeah, you can use pointers to traverse arrays of structures the same way as everything else. Good. So, additional notes on structures. Structure members may be variables of primitive data types or aggregate data types, such as arrays or other structures. So, these guys here, this example just has pointers and integers, right? But the fields of this structure could be other structures. They could be arrays. They could be anything you want, right? The only thing that a structure may not contain is an instance of itself, right? So, and that sort of comes down to the problem of resolving the size of the data structure. So, if we imagine, right, that we had a data structure like struct bogus, right, that contained, you know, an integer x and struct bogus impossible, right? This bogus data structure contains an instance of itself, right? So this is like, under recursion, like a function can call itself, that's fine. But if a structure contains itself, the question is, you know, how do we resolve the size of operation? What is the size of struct bogus, right? Well, it's the size of an integer, so say 32, plus the size of whatever a struct bogus is. So we have to invoke size of struct bogus, right? So we enter the same calculation. It's 32 plus size of struct bogus. That's 32 plus size of struct bogus. So basically, if a struct were to contain an instance of itself, it would be infinitely large, because it's a recursion without a base case, right? Now, so I have a question or a comment. I was hoping you could make structs recursive. Oh, you can still make them recursive. They can't just directly contain another instance of the structure. The thing that it can do, all right, let's say struct non-bogus int x struct non-bogus pointer next, or something like that. Let's just call it next. Technically, I've just constructed a linked list for you, but so although the like this one will fail because there's no way to resolve the size of the structure, because it contains infinite copies of itself, because every copy of its, like every instance of the structure contains at least one more copy of itself inside of itself. So it's literally infinite, right? So you cannot actually compute how big it is. Not to mention, if you were to instantiate it, it would consume all memory in the universe and then still be hungry. However, if you have a pointer to a structure, pointers are of a fixed size, regardless what they're pointing to. That's one of the beautiful things about pointers. So size of non-bogus int would resolve to 32. Let's just say, for the sake of argument, that your memory system uses 64-bit addressing. So the size of the pointer to the next non-bogus structure is 64. So we would resolve the size of operator to return 96 bytes. Or bits, pardon me, bits. Actually, it returns it in bytes. So this would be 4 and 8. So it would be returning 12. 12 bytes. Right? Because it doesn't matter how big the thing you're pointing to is. The pointer itself is always a fixed size. So you can always resolve the size of the pointer, right? That does not impede the size of calculation. So, structures can, and often do, contain references to other structures, but they do not actually contain the structures themselves, if that makes sense. Hopefully that makes some degree of sense. So, a structure may contain a pointer to an object of the same type as the structure. Many advanced data structures, such as trees, rely on this, if you consider trees to be advanced. In some circles, trees are the most basic. This is a recursive or self-referential data structure. Recursively defined data structures are extremely useful. You may declare any number of variables after a structure definition, not just the default shown on the previous slide. You may even omit the structure tag, in our case customer, and declare all of your variables in the global namespace. Question: why do you need to define the size, though? Why do you need to do that? Excellent question. So the question is, the answer to that question involves, what is size of used for, right? Well, when you declare a, so let's imagine, just for the sake of, let's say, just for the sake of interest, you actually wanted to declare a variable of type structure, right? When your program requests a piece of memory which it attaches to a variable, it needs to know how much memory to allocate to the variable. The way that it figures that out is by resolving the size of the thing using size of, right? So anytime you say int x is equal to 7, one of the implicit operations is that the program requests of the operating system a piece of memory that is size of int, right? Same thing goes on with structures. If you have, struct bogus foo, right? If you declare a structure, this is requesting that the operating system allocate enough memory for this structure. In order to allocate enough memory, it needs to know what the size of the thing is. So this involves an implicit call to size of. So, because it involves an implicit call to size of, if size of cannot resolve, because your data structure infinitely includes itself, then you can't even declare a variable, because how big of a space are you declaring for it? You can't know. Well, you can know, it's infinite, right? And no computer can allocate infinite space. It's not physically possible. So yeah. So that's why you need to know the size, because you literally can't even declare a variable of that type without knowing the size. Right? Make sense? Hopefully. These are good questions so far. So, valid operations on structures. Unlike classes in Python and other object-oriented languages, structures have a relatively small number of operations which may be performed on them. This is it. You may perform assignment to structures, so long as that assignment is using this form and every field has been specified, using curly braces. You may take the address of a structure. You may find the bit width of a structure using size of. The size of a structure is roughly the sum of all sizes in the field, but sometimes blank space may be included due to the addressing of small variables. So, basically, I'll just illustrate this quickly. If you have a, let's say you have 8 bytes. Each one of these is a byte, right? Everything likes to line up to the word size of the operating system. So the system itself, let me see, do I have enough in here? No, I don't. Okay, there we go. The operating system itself likes to line addresses up to, like, specific powers of 2. So it's possible that, like, if you declare 3 characters, say, and an integer, that it will, like, the integer will occupy all 8 slots, right? Or all 4 slots, because it's 32 bits. But each character only occupies 1 byte. So it's possible that you'll have, like, these little gaps like this that it'll just fill in with nothing. And so the size of the structure will be counted from one end to the other, including any blank spaces which have been left. If that makes sense. Good. Note, these are operations on variables of the structure type, not the fields of a structure. So once you have accessed the data inside of a structure using dot syntax, all of your regular operations are applicable. So, you know, if you have a integer, you can perform addition, subtraction, multiplication, division, modulus, whatever you want. You just, like, the structure itself, only these operations are applicable. So, for example, if you wanted to dynamically allocate a structure, you would malloc and then size of and then you would write the structure name. A blank space would be equal to 1 byte and just return blank. So no, it's like it doesn't. This blanks, like, this is in memory, right? This blank space, like, it doesn't really do anything. Like, you'd never actually see it. It's essentially it's space that the computer is wasting so that it can do more convenient addressing for itself. You actually don't have to worry about it too much. All you really have to know is that the size of a structure is at least the size of all of the components, because there may be a few small gaps inserted just because of the unevenness of different fields having different bit widths. That's all. That's the takeaway there. So, here's a somewhat longer example. We declare a struct card, which has strings for face and suit. Even though strings don't exist, we kind of pretend they do. Pardon me. So, we can declare a card to be a variable of type struct card. A card.face is ace. A card.suit is spades. We can then have a card pointer, which takes the address of a card. And thank you. Actually, that's not bad in terms of latency. So then we can print out ace of spades 3 different ways, right? So there are actually 3 different, like, under this scenario, we can get at the data inside of the structure using 3 different forms of syntax. Number 1, direct .syntax access on the structure variable itself. So there you go. Number 2, well, I'll go to number 3 first. So we can take the card pointer, dereference it, and then access the fields using .syntax. Or we can use this symbol, which we haven't talked about yet. This is simultaneous dereferencing and field access. So in the same way that square braces are dereferencing plus offset. Arrow is dereferencing plus field access. There we go. In the previous example, you may have noticed a pointer to the structure data type. When you have a pointer to a structure, you access the fields of the structure pointed to using hyphen greater than, which is supposed to look like a little arrow. This is syntactic sugar for pointer dereferencing and field access combined into one operator. So x arrow y is defined as dereference x access y. It is almost always more efficient to pass structures by reference than by value. So that requires maybe just a little bit of explanation. C passes things by value, right? So if you have a large structure, let's just imagine that we're no longer talking about these tiny little toy examples, but something that would actually be used in real life. Let's say you have, you know, a structure containing many variables and many, like, arrays. Let's say we have a bunch of arrays in there as well. If you're passing that whole big bastard by value, then everything in it has to be copied into the function every time the function is used. However, if you use a pointer, the pointer is only one value. It can be copied very quickly relative to the entire data structure. So if you use a pointer to pass things, you don't have to do all of that copying, which speeds up your program enormously. Enormously. It is almost always more efficient to pass by reference than by value when you're talking about structures. You can allocate memory to a structure pointer in the same way as everything else, using malloc or calloc. Don't forget to free. Right? Make sense? Give me a thumbs up if you're good with all of that. Oh, by the way, lectures will resume in person next week. I talked to my wife about it, and she gave me the okay. So next week we're going to be back in person. Good. Wonderful. So, I'd like to shift gears slightly here and talk for a bit about bitwise operations. Bitwise operations are something that you, like, relative to other disciplines, like, relative to, for example, the software people or the comp sci people, bitwise operations are something you actually have to know how to use. They come up quite frequently in embedded systems applications. So, in embedded systems applications, you are very often concerned with the value of a single bit. Whether that bit be inside of a register, whether that bit be, some option that you want to set that's been prescribed for you in a manual. You need to know how to manipulate the individual bits inside of an integer or a character or anything like that. The way that you do that most effectively is through bitwise operations. So, let's review the bitwise operations. I say review, though I have a feeling for a lot of you, you probably have never done bitwise before. Let me just poll people. Have you done bitwise before? Boom. So bitwise means by the bit, where individual bits are the values under consideration, as we shall see. So when we say a bitwise operation, it means that we are concerned with the individual bit values inside, composing the number, inside of the number, all right? So they're really not too hard to understand, like, once you've seen them. Half of them map onto the Booleans, and the others are reasonably easy to understand anyway. So let's go through them in order, then. It seems like nobody has ever heard of bitwise operations before. So a lot of these operations boil down to, like, simple AND gates, OR gates. Like, things break down to, like, logic gate level pretty easily. So, like, while it's, like, maybe you, like, it's convoluted and complicated and you can't quite imagine what, like, the circuit that performs division would look like. For all bitwise operations, you should be able to pretty easily envision, like, what the circuit that performs bitwise AND should look like, right? But anyway, so bitwise AND may be thought of the application of a logical AND gate to each of the bits in the two operands sequentially. Common C applications include bit masking. So, just to remind you what AND, Boolean AND means, it means if both of the inputs are 1, the output is 1, right? So, the way that a bitwise function works, you start at the least significant bit, move up to the most significant bit, examine the bits in sequence, and then compute the result and store it in the result, right? So I think it might be a little bit more useful for me to do this in the notepad thing that I'm working in here. So, let's just create some random numbers, right? So bitwise AND. 0 and 1 is 0. 1 and 1 is 1. Oh, those are tabs. There we go. This will work better. 0. 1, 0. 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 0 and 0 is 0. 1 and 1 is 1. 1 and 1 is 1. That's literally the process. It just goes through the bits one at a time. Just does Boolean AND on them. And that's the result. So the question, applications then. Bit masking. Let me just show you what bit masking is quickly. So let's imagine that you wanted let's say you had a number and you wanted to preserve the values of, say, bits 0 through 3, and you wanted to throw out the rest, right? You just wanted the first, let's do it slightly more complicated. Let's say that you had a number like this one, right? You wanted to preserve the values of these 4 bits in the number, right? Whatever their state is, you want that to be their state in the output, but you want to set the rest of it to 0, all right? This is what you do. You do bitwise and you toggle to 1 the region that you want to keep, right? Anything that's set to 0 in either will end up 0. So this will be a 0, 0, 0, 0. And literally, this will be copied in there. It won't be affected. It will be translated exactly. So that's what bit masking is. Cool? Hopefully. So let's talk about bitwise OR. Bitwise OR is a very similar operation. You can probably see where we're going from here. An OR operation, of course, yields 1 if either of the two inputs are 1. So let's just copy this guy and perform bitwise OR instead. Bitwise OR, the operation is a single vertical bar character. Slight note, you may notice that these symbols line up with Boolean and Boolean OR. Boolean AND being 2 ampersands, and Boolean OR being 2 vertical bar characters. There's a reason for that, just so you know. So, 0 or 1 is 1. 1 or 1 is 1. 0 or... I did it again. 1. 0 or 0 is 0. 1, 1, 0, 1, 1. There we go. So that's bitwise OR. Fantastic. Now let's do the tricky one. Exclusive OR. The caret character means exclusive OR, outputting 1 if the inputs are dissimilar. Excuse me. Common applications include bit toggling and arithmetic addition. Pardon me. So, once again, let's copy all that. Pardon me. So if you look at your truth table here, what does 0b mean in the binary representations? Oh, that's just like this is a binary literal in C programming. That's all that means. This just OB just means this is a binary number. Good question. Thank you, Marco. So, if we take a look at the truth table, this is what these things are called, by the way, is truth tables. So X or Y is 0 if the inputs are 1 and 1 or 0 and 0, and 1 otherwise. So, if we were to compute this, these are different, so it's a 1. These are the same, 0, same, 0, same, 0, different, 1, and then same, same, same. And that is XOR. Good. Make sense? Hopefully. So applications include bit toggling, right? So basically, if you have a number, right, and you XOR that with, some region of it, you've XOR'd it, right? The region which you have which you're XORing zeros with, that will remain the same, right? But the region that you have not XOR, the region that you have put 1 in, the bits will flip. So 0, 1, 0, 1. And, interestingly, if you apply the same operation again, then you get this region being the same, and it flips back to the way that it was before you did the two XOR operations. So this is like commonly how you can get like LEDs to flash alternately and stuff like that. And while we're on the subject of bitwise applications, we're out of time. This one will be quick. While we're on the subject of bitwise applications, for the bitwise OR operation, if you remember how, like with AND, bit masking allowed us to select a particular region with the rest being zeros, right? If you invert the if you invert it so that the region you want to preserve is 0 and the rest are 1s, and you're using bitwise OR instead, then you get the opposite effect. So everything outside of the region that you specified specified as being 0, that all gets flipped to 1, and then inside of this region it gets saved. Basically, it gets preserved. Right? So if you want zeros in the background, use this for bit masking. If you want 1s in the background, use this for bit masking. Make sense? Any questions? Okay, well, I guess I'll see you next time.